Hi, everyone. Thanks for joining us today. We're going to give folks a few minutes to get started, so please hang tight and we'll get started soon. Okay, good morning, good afternoon, good evening, depending on where you're joining us in the world today. Welcome to today's CNCF webinar. I'm Christy Tan. I'll be moderating today's webinar. Today's webinar is comparing eBPF and Istio Envoy for monitoring microservice interactions. I'd like to welcome our presenters today, Cruz, Solutions Engineer at Flowmill, and Jonathan Perry, CEO at Flowmill. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop in your questions and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinars page at cncf.io/webinars. With that, I'll hand it over to Rocco and Jonathan to kick off today's presentation. Take it away.
Great. Welcome, everyone. Thank you so much for joining us here today. So first, just, as we already kind of talked about, or Chrissy had already mentioned, there is the KubeCon Cloud Native EU event coming up. More information on that, and there's a link inside of the chat. I'd like to introduce Jonathan Perry. Jonathan, if you want to do a quick introduction. Sure.
Hi, everybody. I'm Jonathan. I'll tell you a little bit about my history. I started building observability solutions in the mid-2000s when I was serving in intelligence. In 2010, I joined MIT and did my PhD on systems that can collect, process, and analyze massive amounts of telemetry with low overhead. And we focused on network monitoring and network scheduling. We interacted with Facebook and had a collaboration where we deployed some of these systems in production at Facebook. And that is where I met the kernel team at Facebook. Facebook has an exceptional kernel team, and I had been lucky to interact with Alexei Startortov, who is the core maintainer for eBPF. And through those conversations, we saw the huge potential that eBPF has in monitoring how applications, microservices, interact with the infrastructure, be it the compute infrastructure and the cloud infrastructure. Are there packet loss? Is there DNS failure? Is there high latency? So both how applications interact with the infrastructure and how applications interact between themselves. So seeing kind of HTTP errors, HTTP latency, and so on. And through that, we got the idea to build systems that use eBPF to get this kind of visibility. And I founded Flowmill, and I hope to tell you more about eBPF during this webinar.
Great, thanks, Jonathan. I'm Rocco Cruz, Solutions Engineer here at Flowmill. I have a history with working with large-scale distributed systems, spent many years at Cloudera building large-scale big data systems, and then also time at Cockroach Labs building large-scale distributed databases that have spanned the globe. So with that, let's go ahead and get into the presentation. So we're going to talk about the two different approaches to observability today. First being using a service mesh, and we're going to mostly focus on Istio and Envoy for sort of the comparison purposes today, and then the extended Berkeley Packet Filter, or eBPF approach. So we'll talk about the benefits of a service mesh. We'll just kind of highlight those. I imagine a lot of people are pretty familiar with the benefits, the metrics that we can actually get from a service mesh, the different considerations. And then we'll also talk about the different approaches on eBPF, go a little bit deeper into that, and the metrics and information that we can get by using something like eBPF. So benefits of a service mesh. This is just kind of a very high-level summary. There's many other great presentations out there that talk about the very low-level benefits and implementations of using a service mesh. But primarily, we see people implement it for traffic management capabilities, to be able to have circuit breakers, different timeouts and retries, and A/B testing. We also see a lot of people deploy service meshes for security purposes. This definitely is something that is worth considering when deploying a large-scale Kubernetes cluster that might have a number of different groups or organizations using that cluster, making sure that you have proper authentication and authorization across the different services, and also that you're using TLS encryption across all of those connections as well. And then the last one, which we're going to be mostly focused on today, is the observability side of using a service mesh. So getting information about tracing, which we'll talk, we won't talk too much about tracing today, but more about the monitoring and the interaction between those different services. So the monitoring aspect of the observability side of things. The kind of high level architecture, as most people are probably familiar with or aware, is that there's really two portions of Istio, specifically the control plane and the data plane. The control plane is not what we're going to be focused on today. It's mostly going to be a focus on the data plane, really talking about the use of Envoy as a proxy, the monitoring of that ingress, egress traffic, and just sort of what happens with the interaction of the services and things from that standpoint. When you do use a service mesh in this way. So let's talk about the different metrics. This is really what we see a number of people use a service mesh for, is that they want to be able to understand what's happening across their different services that are deployed to the cluster itself. So for HTTP and gRPC interactions within the cluster, we can get information about the different or the number of requests that have come in, the duration of those requests, the size of the request and the response. And this is all information that then can be easily exported out to Prometheus and then use something like Grafana to actually look at that information in more detail. And then for TCP traffic, we're a little bit, we can't get as detailed information. So we are limited to just being able to see the bytes sent and received and connections that are open and closed. So, we're getting more kind of high level information, for when we're talking to things like Kafka or Redis or, other things that are not implementing gRPC or HTTP in that regard. So, what we kind of highlighted there previously are really the application level or application layer specific metrics. So, we're seeing, these are metrics that are definitely very useful and very helpful. And, one of the things I failed to mention on the previous slide is that, that information, although these are the particular metrics that are provided and just kind of the high level counters, there's a number of labels that go with these metrics that will provide you information from which service actually made the request to the service that it made the request to, and things from that perspective. So you can do a lot more analysis than just sort of the high level, gathering counts and durations and size on a per server basis. You can do this down to the pod and individual, for those individual services. But going back to this, that's still application layer metrics. The one thing that is missing from this is actually the network layer. So, these network layer metrics are not quite available in a service mesh today, or at least with something like Istio and Envoy, is really being able to capture the protocol level or network level metrics around round trip time. So actually seeing the latency for TCP itself. Also seeing retransmissions that are happening at the TCP level and also for packet loss. Also capturing UDP traffic as that occurs, and that could definitely be something used for video streaming services and things from that standpoint. And also DNS as a protocol as well, where quite often we have seen issues where DNS has been problematic for particular deployments where DNS latency might be really high for looking up of particular services or names, or you might actually see failures in DNS, but it's not completely obvious right off the bat that those failures are occurring in the application. So those are network layer metrics that we're not seeing today inside of a service mesh. So Istio Envoy, they're really primarily designed to provide this application layer metrics, which they're key and critical and important themselves, but it's also very important to understand the network layer as well. You know, if you were deploying these applications in an on-premise type environment or an environment where you control the network, you could have visibility into this information by looking at data coming from your switches and routers and things that you might have on premise. But now as you move to the cloud, or most people are moving to the cloud for their Kubernetes deployments and such, when that occurs, you don't have that same level of visibility into the network. You can't see, you know, if there are TCP issues that are occurring or going across, you know, the routers or switchers in that network. So having visibility into this is really key to understanding, you know, what could impact your application or services. You know, you might all of a sudden, and we've seen this a few different times in a few different places where, you know, the network between different zones within a given region might become unstable, or there might be a large number of retransmissions, you know, and trying to attribute or seeing that as sort of bubble up into an application issue, trying to attribute that to the application or to the network is definitely key and critical when troubleshooting those types of issues. So to get to that level of information, you have to use something like eBPF to get this more detailed network data. And Jonathan will talk a bit more about eBPF and how that works. But first, we're going to just talk a little bit more about a service mesh and sort of the overhead that a service mesh deploys. So, you know, a service mesh provides a lot of functionality and provides, you know, a lot of benefits. But with those benefits, definitely comes overhead that we have to occur. And it's always critical, and it's always, you know, it's always very important to understand what level of overhead are we paying, or, you know, are we going to see when trying to, you know, when deploying a new service or using a service mesh in our environment. For this particular sort of comparison or benchmark that I did, I wanted to use something that was a little bit more of a realistic type of service or realistic set of services. So I actually made use of the very well put together Google Cloud Platform microservices demo. It's a set of it's a handful of different services that call each other whenever a transaction occurs. It also has a Redis backend as well for doing retrieval of data and storage of data. So there's a number of different service interactions that are occurring within the system. So we set up just a very simple 3-node EKS cluster inside of AWS. We made use of C5 extra large instances. And then also we deployed the latest version of Istio at the time of which I ran the benchmark, which was a month or so ago, using version 1.6.5. We made sure to use the default profile. You know, a lot of times when people are trying Istio out, they'll use the demo profile that comes with a lot of other great sort of tooling and other components to allow for further kind of introspection of data within the system. But we went with the default, which is what's recommended for production level workloads. And then the thing that's also fantastic about this particular bench or this particular microservices demo is it actually comes with its own load generator, which is Locus. So instead of running Locus as part of the application itself, we actually moved Locus to its own separate instance within the same region of the Kubernetes cluster. And we were simulating 500 users using Locus, which is using the pattern and sort of the configuration file that's defined by this microservices demo. So this is something that you could very easily reproduce yourself and easily run this particular benchmark within your own environment as well. So with that type of setup, we went ahead and started to benchmark the application. So the other great thing about this microservices demo is that it can be deployed with just sort of a normal sort of standard configuration. And then it also does come with the additional Istio configurations too as well to be deployed using Istio for ingress and for the interactions of the services. So we first deployed it without, just sort of as a baseline standard application. And across the cluster, we saw about 13% CPU utilization and a P50 response time of 16 milliseconds. For our P90 response time, we saw about 33 milliseconds. This is about standard, about kind of what you would expect for an application like this, where there's a number of interactions and things from that perspective. It kind of in line with sort of what you would expect out of it. We then redeployed the application using or deployed Istio to the cluster, redeployed the application to make use of Istio, and then reran our tests on the cluster as well. And what we saw for CPU utilization is we saw a increase of nearly 70% for CPU utilization. Now, with a smaller cluster like this, there is definitely additional sort of overhead that is paid a little bit more for a smaller cluster versus if this was to scale out to a larger cluster. But it does go to show that there is a significant increase in overall CPU utilization for the application once Istio Envoy was deployed to it. The other place that we saw pretty large gains was around the P50 response time. We actually saw it go from 16 milliseconds to 25 milliseconds. So, over a 50% increase. And, this might be something that, for particular use cases and workloads, this might be perfectly acceptable. For others, you might want to try to minimize your latency as much as possible. So it's really just sort of that, making that consideration or taking this into consideration of, the additional latency that could possibly be added when using something like Istio Envoy for your application. We also saw a P90 response time of about 48 milliseconds, which is 45% increase over the baseline application. So, definitely, non-trivial increase in overhead and in latency that, was added for using Istio. And, it gives you kind of a general idea of sort of what we saw when, we deployed the application, just with the baseline versus using Istio and Envoy. So with that, let's talk about eBPF and how eBPF could be used. And for this section, I'm going to hand it off to Jonathan so that he can take us through that portion of it, and then we can go from there. Jonathan, if you want to take over.
Great, thank you, Rocco. So eBPF, let me tell you a little bit about it. eBPF has been around since 2013, 2014, with the introduction of the BPF system called Kernel 3.18. So this has been around for a while. Since Kernel 4.4, there has been enough BPF support machinery to write substantial programs. And this has been backported to Rails 7.6, so kernels as early as 3.10. What BPF allows user space programs is to run tiny snippets of code when different kernel events happen. So it could be when a packet is received or when a process is started, a container is started, a container finishes, and so on. Any kernel event you can run some code on. This is great for telemetry collection because you can use eBPF to get from the operating system a stream of important events where kind of you choose what events are important to you. And you can get a stream instead of trying to recover this information from the operating system using command line tools or other system calls. Which could be really expensive in number of CPU cycles and give you incomplete information. eBPF also gives these visibility platforms more access into internal data structures. So it is possible to get information about how the system is behaving, what is happening to your sockets, to your processes, to your containers, that is just inaccessible from user space. BPF is great because there are very extensive mechanisms to make it safe and fast. Safety-wise, eBPF, the kernel comes with an in-kernel verifier. it's a mechanism that as you load eBPF programs, the kernel makes sure that first, there are no infinite loops in it. Those are not allowed. It cannot access invalid memory and crash your system. And in fact, in many of the settings where you want to extract telemetry, eBPF code runs in read-only mode. It cannot change any memory in your kernel. So this has great stability benefits, compared to kernel modules, for example, where you can get similar visibility. So eBPF is extremely safe. It is also very fast, low overhead. The kernel has a just-in-time compiler that transforms the eBPF code into very efficient machine code. So you can run this, you can run instrumentation very pervasively with very low impact on your performance. There are open source projects that provide some BPF tooling. One of them is BCC. That is a major project. I encourage everybody to go and visit it, read a little bit more. And BCC has a set of tooling that they provide as examples of how you could use BPF and real command line tools that you could use. And for example, for networking, you can get, there are tools that allow you to get information about a stream of notifications of new sockets. You can get information about packet drops, SYN timeouts, retransmissions, and summaries of sockets in the system. I'll show you a demo of one of these applications in a moment. I have instructions on here on how to run a demo. There are containers available that where you can just spin them up and run some BCC commands on your system. So on the left-hand side is that command if you want to try it yourselves on your cluster. What I'm going to show you is this command line tool, TCP-top. TCP-top instruments the receive and send paths for TCP. And this is how it looks. So we run TCP-top on the microservices demo that Rocco was talking about. You get a huge stream of data out of it every second. And here you can see the different processes. Here's the front end that used and how many packets were received and, sorry, how many bytes were received and transmitted. I know that it was fast, but trust that you get IP level information and information about the amount of data that is transferred. Just a word of a slight word of caution when building BPF tools. Here on the right-hand side, I've included some of the Python code that reads from BPF in the TCP-top tool. You can see here IPv4 send bytes is the object that is used to read information from BPF. As you build this tooling, you need to be careful that you need to be careful of races and how you read the data in a way that is consistent. For example, here, what could happen is the for loop runs and this Python program reads information from kernel data structures into this, this dictionary, IPv4_throughput. As it's reading, you should notice that kind of the kernel data structure might update. There might still be traffic on the system. As the loop finishes, the code clears the kernel data structures. But what could happen is, what does happen is, you could lose some events that go into these data structures as kind of between kind of the beginning of the for and the clearing of the data structure. So you can get incomplete data. So these are the types of things you need to worry about as you build instrumentation. But once you handle those, instrumentation can be extremely low overhead and high performance. So we've mentioned a lot of we've been talking a lot about getting network information, kind of infrastructure visibility using eBPF. I just wanted to note that it's also possible to get application layer information using eBPF. So you could build systems that get you comparable telemetry to Istio. It's not only about complementing it. You could potentially get information that's very similar to what Istio gets. So here on the left-hand side, I've shown how you can use the Go tooling in order to get symbol information, function information from inside one of the binaries. This is a hello world web server that you can query. So here you can see some of the functionality from NetHTTP. And on the right-hand side, I've shown a run of funcount, which is another BCC tool that allows you to, in this case, just count how many times each function is called from, in this case, NetHTTP header. So this kind of using this type of visibility into eBPF, you could these eBPF handlers could potentially read more about user space programs like error codes, the endpoint that that is being queried, the sizes of transactions, really the same as what an Envoy or Istio would be able to get. So this is like eBPF is really powerful, not only for infrastructure metrics. And with that, I'd like to hand off back to Rocco to show you some of the measurements on BPF code.
Great, thanks, Jonathan. So what we ended up doing is we took TCP top that Jonathan had mentioned earlier, and we actually started up a container on each node within our Kubernetes cluster, capturing the output from that running every second in that environment. And we then reran our benchmark. So we have our baseline application here that's listed. And then, what we saw from a CPU utilization is a 1% increase or 7% change from that 13% to 14% CPU utilization across the cluster. A lot of that was primarily due to the Python side of things, of reading the data and putting it out to the screen. But there is also the trade-off too that the information wasn't being collected or sent off. But it is definitely critical to understand that there is the eBPF portion of it is a very small portion of the overall overhead to collect these metrics and information. The real key thing though is that this introduced no additional latency for collecting this information. Now it is to be noted that you're not getting the same level of benefits when using something like Istio Envoy to actually do authentication and traffic management and things from that perspective. But if what you really care about is the observability side of things, using something like eBPF can really help with not adding additional latency to the application if you're using something like eBPF to actually monitor the different network interactions that are happening within the system itself. And the same is true for P90 response time. We saw no change or no effect on that for the particular system as well. So, at this point, what we really just wanted to show is that the service mesh brings a lot to the table. There's a lot of benefits with deploying a service mesh. There's many strengths that we have talked about. The detailed application metrics are definitely useful, especially understanding long-lived connections and making sure that they're balanced across the system and things from that perspective. Security, encryption, and traffic management are all really key things that are very important or great things that you do get with using a service mesh. But there is that resource overhead that you do have to pay for having a service mesh deployed. Also the increased latency, which I think for some applications might be perfectly acceptable. And then for others, it might be something worth considering if that additional latency can be tolerated for your particular application. And then also the network layer metrics are not readily available with something like this, which, especially in cloud type deployments, as we mentioned earlier, is really what, it is really something that there's a lack of visibility into. There are some solutions from the different cloud providers for getting network level information, but it's normally more summarized around transferring of data, not so much the errors or retransmissions or things from that perspective. And getting to that information can typically be pretty difficult or pretty costly in the sense of if you were on something like Amazon with using flow logs or VPC flow logs, capturing that information and sending to S3, is definitely an additional cost as well. Now on the eBPF trade-offs, the strengths are, there is, since we are running at the kernel level and capturing events at the kernel, there's, we can get very detailed network layer metrics. It can be very optimized for minimal impact since we're, just reading sort of events or capturing events as they occur within the system. The weakness is like there is no full open source solution for capturing and using this information today. There are some projects out there like Psyllium and such that are making use of eBPF to help with portions of the service mesh, but just the tooling, just focusing on the observability side of things, there's not a there are kind of pieces out there today, but not a full solution that's available from the open source project. So bringing it all together, using a service mesh along with eBPF really allows for that deep observability on both the, from a application standpoint and also from a network standpoint. So being able to combine these metrics from both systems, it really provides you sort of a complete view of the environment. If you can actually take a look at the application level metrics coming out of Istio Envoy, and then use that to sort of correlate that with the information that you can get out of eBPF for the network side of things, this really gives you the ability to see kind of a complete picture of how the systems are interacting. Are we seeing increased are we seeing increased errors because there's a number of retransmissions? Are we seeing increase in TCP latency in the environment? Things from that perspective, which, using the combination of both these metrics, you could easily get to the bottom of, is this a network level issue or is this a application level issue? And eBPF itself can also help with identifying issues within the service mesh. The service mesh components are talking to each other as well across the network. If there are issues with the network from that perspective, being able to actually capture that or see that with the tooling like eBPF is also really critical as well. So with that, hopefully we've at least kind of given you a bit of a taste of what eBPF can do and the possibilities around eBPF. We're here at Flowmill, we're actually working with eBPF to bring network visibility to different network applications. So if you have any further questions on eBPF and what can be done with it today, we'd be more than happy to answer those questions for you. And if you'd like to follow up with those questions directly, you can contact us at info@flowmill.com or ask any questions that you wish in the Q&A section here as well. So with that, we'll take a look and see if there's any questions that might have come up during the process. Jonathan, I'm not sure if you've been monitoring.
I've been monitoring. We have 2 questions. Let me ask you one of them by TJ. So do you know if the Istio overhead came from adding MTLS?
We did not get down to the specific components of what added the overhead. This was, so we didn't disable or enable MTLS. This was the default profile, just how you would normally run Istio Envoy out of the box. So unfortunately, we did not isolate the specific exact components and in which component added which amount of overhead to the system.
Mm-hmm. I can tell you from experience. So Rocco did the measurements, but we run TLS encryption. We've done a lot of work in our systems on TLS, and the act of actually encrypting traffic is not substantial. Usually, you pay a handful of cycles per kilobyte, not a handful, hundreds of cycles per kilobytes. It's not going to be something that changes your performance, but the act of intercepting the traffic and processing it in another process, what Envoy does, from our experience, that does have higher overhead. So I don't know, it's not a definite answer using data, but I hope it gives you some our intuition onto where overhead is coming from. That is not the actual encryption, but having the sidecar in there. Let's jump to the next question by Avi. The question is, can eBPF give application layer observability for languages other than Go, and which languages are supported? Rocco, I don't expect you to answer while you were talking. I pulled up some of the BCC examples, example tooling, and the BCC repository has tools for, let's see, Java, Node, Perl, PHP, Python, Ruby, and TCL. And we've had experience with Go and C++ ourselves. I know that there's an OpenSSL tooling in BCC that uses kind of just libraries and written in C++. So there's the impact you can have with application level eBPF observability is quite wide in terms of languages. Let's go to the next question. Maybe I'll ask you, Rocco. To use eBPF, do we need code changes? By Jindong.
Yeah, and you could probably answer that too as well. The answer is no. So eBPF is something that is more of a passive system. So to deploy it within within an environment application, no code changes are needed for it to actually monitor the network layer or to monitor things that are happening within the application space.
Great. I'm going through these in order because we have maybe a few of them. So instead of trying to jump around, let's do the next one by Shibashis. I hope I got your name right. Can we run eBPF tooling without additional privileges in pods, running data plane of the clusters?
Jonathan, you'd probably be the better person to answer that, but my understanding is that you do need to have additional privileges or you do need to run in a privileged state to gather this information.
Right. I'll just add the color of the eBPF tooling does need additional privileges, but you don't need to run it as a sidecar. Frequently for example, Kubernetes environments, you run it as a daemon set. So the daemon set needs to have additional privileges, but in the pods actually serving traffic and doing data plane processing, those just run normally. They don't need extra permissions. I hope that answers the question. Let's see, I'll just go in order because I haven't read it yet. Can you comment on ability in terms of availability, permissions, and compatibility to deploy eBPF filters on serverless platforms, such as AWS Fargate? And what about container optimized operating systems, such as BottleRocket?
Sure, Jonathan, do you want to take that one?
Sure. So the eBPF does require kernel support for eBPF. This needs to be enabled in the operating system, and indeed, we've encountered most of the distributions out there enable eBPF. So you could use it on Ubuntu and AWS Linux and so on, Debian, Red Hat. With serverless platforms and optimized container operating systems, I don't have information about BottleRocket specifically, but with serverless platforms, those are closed. They don't give user space programs access to the operating system. So with those, you'd need a different mechanism in order to get visibility. Luckily, with techniques such as we talked about to get network visibility, you could get network visibility from if you have communication going between serverless and non-serverless components. You can get the visibility into the serverless side of how it interacts with the infrastructure through the side that is not serverless. Right? You only need to be on one side of the connection to get good visibility into how your applications are behaving. But we are working with AWS to get better support into better eBPF support or any eBPF support for Fargate and Lambda. Great. Okay. I'm going to jump a little bit down. Ravish asked, are you aware of any additional overhead it can add if we use something like Spire Spiffy or Spiffy with Envoy?
Not that I'm not very familiar with that, so I couldn't speak with much authority to that, unfortunately.
Yeah, I don't have information about overhead for Spire or Spiffy. I know Citadel and Istio could have some. Well, I think Citadel has an alternative implementation. I just don't know. Yeah, I'm not familiar. Sorry. Najendra is asking, can Istio or eBPF also detect the failures and the reasons? Root cause. I'm trying to parse this, right? Like detect the reasons for failure or information in the applications or containers like or the containers where the applications hang or infinite loop or etc.
Yeah, so it's a good question. A lot of the times we found that the root cause for a number of systems where there might be high TCP latency or that connections were closed or refused is that typically something has happened where we're either limited on CPU or we're seeing high disk latency or things from that perspective from the underlying container that we're calling to. eBPF does have ways to actually capture that information too as well with not a huge amount of increased overhead. So it is possible to use something like eBPF to further troubleshoot the issue. It's always hard to get to the exact root cause because root cause could be a combination of resource starvation or could be other application level specific issues that might have occurred within the system itself. But definitely eBPF could be used potentially to get further information on the resource starvation issue that you might see in particular deployments.
Right, and the second half of the question is, does Istio or eBPF provide recovery mechanisms for applications or the network?
I'm not, not completely familiar with what could be done for Istio or Envoy. There is always ways. There are always mechanisms that could be implemented to, kill non-responding containers. But that's always something to make sure that you don't do too lightly, because if they're killed for the wrong reasons, you could increase your chances of a cascading failure if you don't bring up sort of resources elsewhere to take on that load as you do as you do go and kill those particular resources in the environment. So that's something not to be done lightly, and making sure that that works as you would expect it to before deploying any kind of mechanism that would try to do an auto recovery of any particular issue.
Okay, I'm gonna jump a little bit. I hope I'm reading the name right. Gregor, are you building your solution with BCC only? Do you see kernel header presence as a problem? And do you think kernel header, so okay, I'll just read the question. Do you think Weaveworks TCP tracer offset guessing solution as something to build on? I think I'd like to take this one. So usually when you use the eBPF code, the kernel data structures change between versions. They change slowly relatively, but they do change. So as you build your instrumentation, every kind of the user space program that inserts the eBPF code frequently recompiles your eBPF code with the kernel headers of the particular system that you're on, so that it knows exactly where to fetch the different pieces of telemetry. And Weaveworks has kind of a very innovative solution called with their TCP Tracer open source project. TCP Tracer just does TCP tracing. And what it does is it tries to understand the structure of kernel data structures in order to so that it doesn't need kernel headers. It kind of tries to find where the kernel is storing different pieces of data inside the socket data structure. I personally, like, technology-wise, this is an amazing solution, and I would have loved not to require kernel headers when running eBPF code. But it has its problems where you can build solutions that are very specific to, let's say, only the sockets. But as you try to build more and more visibility into more data structures, you want to see how processes are behaving, how containers are behaving. You really need that information in order to know per socket what is the pod that it's accessing. There are a lot more data structures that you need to touch, and the offset guessing just doesn't scale there. It's hard to do, and it's very hard to do with pointers. So following kernel data structure just becomes extremely hard with this kind of solution. So we like to have kernel headers, and we've built tooling to automatically fetch kernel headers on multiple distributions in a resilient way so that it's easy to install eBPF code. And we believe that's the right way to do things, our current state of thinking. Christopher asked, is Flowmill applicable to L2, L3 network service meshes?
Do you want to take that one too, Jonathan, if you don't mind?
Oh, I guess. Let's see. Yes, definitely. What you get from a solution like Flowmill or through eBPF, I won't talk specifically about Flowmill, although Flowmill has these properties, that you can collect deep information about how the application is interacting with the cloud infrastructure, the network, and the operating system. So even if you have a service mesh that forwards TCP or IP connections, the visibility that you get from eBPF is still valuable, and you can get it even if you're running a network service mesh. I hope I answered the question. To answer it in a different way, I don't think there's anything in a L2, L3 network service mesh that precludes hurts the visibility from Flowmill or eBPF. I have a question. Why should PID namespace be same as the host PID namespace, right? Like when you have containers, container PID namespaces versus the host PID namespaces. I think I should take it, Roko. I'm sorry. We tackled this maybe a few months ago. So the question is, when you have processes running in containers, frequently C groups has it isolates the container from knowing the other processes running on the system. What you do when you run BPF code is, when you traverse the kernel data structures, you can read both the PID from the namespace of the container, but also each process has a process ID in the global host namespace. And so when you write eBPF code, you need to decide which one you want. Frequently, you want the host PID namespace, because then you can also tie it to C groups in the PID name in the host root namespace. And so the answer I have is you can choose in eBPF which one you read, and depending on what you want to do with it, and frequently you use the host process IDs. Okay. So Shibasish asked, when you run as a daemon, are you suggesting entering pod process namespace using tooling like nsenter? I think this is relevant to the previous question, right? Like, how do you gather the right namespace for processes? So yes, what we usually do is we ask for the daemon to run in the host PID namespace to begin with. That simplifies a lot of things, because as you write tooling, you want to use eBPF in conjunction with, let's say, the proc file system. So you want your observability solution to be in the global namespace, so you can cross-reference the process IDs you get from eBPF with things like you read from proc. So definitely, yes, the daemon set you should consider running in the global process namespace. Great. I have a question from Rajaval. I'm sorry, I'm jumping around a little bit. eBPF, will it provide network isolation?
So the eBPF is more of, as Jonathan had mentioned earlier, a read-only mechanism. So it's not going to do network isolation or sort of kind of interact or impede the applications themselves. It's more going to collect information on what's occurring within the system.
Great. Can I jump to Nagendra's question? I'll go back to the Cilium question in a moment. Do you have stats on overhead of Istio or eBPF in a distributed environment? So when containers are deployed across regions?
No, this was a single region deployment. So we haven't tested. Normally you wouldn't run a Kubernetes cluster or an environment across multiple regions. There is the possibility of doing federated Kubernetes clusters, or you can have shared namespaces across different Kubernetes clusters in different regions. But we didn't test that particular setup. This was nodes deployed across different AZs within the same region.
Right, and I'd like to add to that kind of we have run eBPF in distributed environments across regions where you have multiple clusters, multiple Kubernetes clusters. So each one is in each availability zone. We haven't seen that the approach has higher overhead, at least eBPF. We have not seen evidence that you have higher overhead because you're running across regions, right? eBPF instruments each individual operating system individually from others. It's just that you need to crunch the data together from all your regions in order to get a global view of how your deployment is happening. This you can do. But it doesn't change the overhead of collection from eBPF. I hope that's useful. We have questions about Cilium and CNI. CZ Huger and Sudeep too asked two questions. So one of them is, do you use or have you tested Cilium with Istio? So Cilium is an eBPF boosted Kubernetes, right? That's the clarification there. And
oh,
and the complementary question is from
Sure.
Sorry, just go for it, Robco.
Yeah, so we haven't tested the Cilium portion of it. It's definitely a very good question. We would expect that the overhead would be fairly reduced using that because of the fact that you're not having to you're not putting sort of a sidecar into the system, but we have not tested that specifically at this moment in time.
Great. I'm going to take Ivan's questions about WASM versus eBPF. I'll need to do some research. I'm sorry, I don't think we have an answer off the bat. Ravi asked, will Flomo work when DPDK and VPP technologies are used for networking? I think I can take that, unless Rocco, if you have a...
No, please.
Your answers are frequently better than mine. The instrumentation you can get with eBPF, again, I don't want to answer like specifically for Flomo, but I'll answer Flomo and eBPF, right? Like you would want a lot of the instrumentation. The added value from doing eBPF in the kernel is that you have access to kernel data structures on the socket. The operating system knows how the sockets are experiencing the infrastructure, how many packet loss they're experiencing, how many TCP retransmission holes they have in their socket buffers. You know, what is the round trip time? It has very good information about what's happening. With DPDK and VPP, those are technologies that process individual packets. They don't have socket context. So while you could potentially write your instrumentation to work on individual packets, like the same mode as DPDK and VPP, I think what many operators should consider when they're using eBPF, and what we've done with FlowMill, is leverage the operating system. You don't want to build a solution that tries to work on raw packets, because the overhead is just going to be huge. There are other companies, I won't name names, but some companies have tried to use packet traces in order to get visibility, and they have had, you know, 10% plus overhead, 10% CPU on the machine overhead for running those packet traces. So it just gets so expensive, and you just lose all the context, and you have to do a lot of work to reassemble it. So we advocate for working in the place where the sockets are terminated. We believe that gets you good visibility. So not in the middle of the network in the DPDK and VPP.
So Jonathan, I know we're reaching.
Mm-hmm.
We have about 2 minutes left, so so we might want to just wrap up here pretty quickly, unless there's just a really quick question you want to finish up with.
I think maybe we should. Thanks everybody for the questions. I think with 2 minutes to go, we have a hard stop at the top of the hour. Christy was helping us set this up. So I want to thank everybody for coming, and thank you for the great questions.
Yeah, thanks again, Rocco and Jonathan, for a great presentation, and awesome to see the discussion here. Just a reminder to folks that the recording and slides will be posted later today to the CNCF website. Also, if your question wasn't answered, there's a link here of where you can contact our presenters, but we'll also be in touch with anyone who has any burning questions. Anyway, again, thank you all for attending. We hope to see you at a future CNCF webinar, and also hope to see you all at KubeCon Virtual. Thanks, everyone.
Thanks, everybody. I'd love to interact. If you want, please reach out. Reiterate what Christy said.
Thanks all.